Oh, I read this wrong.
Okay, so let's go ahead and get this review underway. Again, the exam's tomorrow. It covers all of Chapter 5. I didn't have a chance to get this typed up until late last night, so I figured I would just pass it out. This will just be a summary of all the topics and objectives, things you should be able to do for the exam. Okay. First thing I want to do though is I want to talk about reference angles, just because I'm seeing a lot of the same mistakes and notational issues. So I want to do an example of finding, I don't know, sine of, let me just make this up. I gotta think of something that ends up being, so say I wanted to do sine of minus 210 degrees and cosine of minus 210 degrees. Specifically using reference angles. Okay. My biggest issue that I'm having is I'm not really seeing people use the reference angles appropriately. Like, I get that you're finding the reference angle, but to me it still seems like people are using the unit circle and memorizing all the values around the unit circle. Remember, if you're going to use reference angles, the only part of the unit circle you should be using is the first quadrant. So if this is 30 degrees, 45 degrees, and 60 degrees, this is 0 degrees, this is 90 degrees. I can give you all the points. That's 1, 0. This is root 3 over 2, 1/2. This point is 1 over root 2, 1 over root 2. And this point right here is 1/2 root 3 over 2. And then, of course, 0, 1. Okay, so if I'm going to use reference angles, I really only need to use the first quadrant in the unit circle. If you look on the review, I don't know if anybody still needs that packet. Is there anybody that still wants a... So all I did is I went in the back of the book and printed off the big giant review for Chapter 5. And then Jesse, Gerardo, Wyatt, I have some stuff to pass back to you, so if you could just come get it before class is over on your way out. Okay, so on that review packet too, I just drew a picture of the unit circle and labeled all the points in the first quadrant for all those special angles. And then of course you could, make sure if you know all these special angles in terms of radians, it's kind of helpful to know all these conversions. So 30 degrees is the same as pi over 6, 45 is the same as pi over 4, 60 degrees is the same as pi over 3 in radians. Okay, so say I want to do sine of negative 210 and cosine negative 210. And I want it specifically using reference angles. Okay. So if you recall, sine of theta is the same as plus or minus sine of the reference angle. Same thing with cosine theta. It's plus or minus cosine of the reference angle. And then it just depends on the quadrant the angle's in, right? For sine, if you're in the first or second quadrant, you're going to do plus sine of the reference angle because sine is positive there. If theta's in the third or fourth quadrant, you're going to choose the minus sign. Cosine is positive in the first and fourth quadrant. So if the angle I give you is in the first or fourth, you choose the plus and you do cosine of the reference. And if you're in the second or third quadrant, cosine of that angle will be minus cosine of the reference angle. So I specifically want to see the notation. So let me show you what I mean. So first of all, you might want to draw, I don't know, a picture of the unit circle. Negative 210 degrees, well, I can start at the positive x-axis and go minus 180. And if I go an extra 30 degrees, this would be well, let me do it this way. This is going to represent my minus 210 degree angle. And then what would be left over for this angle over here? So yeah, if you go minus 180, you have to go an extra 30 degrees to get to the terminal side of the angle. So this is what I want to see with the notation. Okay, the reference angle is 30 degrees, so I want you to literally write sine of negative 210 is sine 30 degrees, and then write the correct sign in the front. Okay, well, like I said, if you're in the first or second quadrant, the y-coordinate of that point will be positive. So sine negative 210 degrees is equal to sine 30 degrees, and this equals 1/2. Okay. I want to see that notation. I want you to say sine of the angle equals plus or minus sine of the reference angle. If you just write sine of negative 210 equals 1/2, I'm not going to be able to give you full credit. I need to know that you're using the reference angle. Okay. Same thing with cosine. If I want to do cosine minus 210, that's going to be plus or minus cosine of the reference angle. So I know I need a cosine 30 degrees over here. I just have to determine the sign out front. Well, if you're in the second quadrant, the x-coordinate of this point would be negative, so you would do minus cosine of the reference angle. In this case, you'd get minus root 3 over 2. Okay. So I need to be seeing you write sine of theta is plus or minus sine of the reference angle. Okay. Anybody want to do one more, or is that kind of enough to let you know what I mean when I say find the value using the reference angle? All right. So any other questions? Any other topics? So you can look at that list. 5.1, right triangle trigonometry. If I give you two sides of a right triangle, you should be able to find the values of all 6 trig functions as well as the angles inside the triangle. Huh?
Look at angles of elevation.
Okay, and then the second piece is angles of elevation. So these are these problems where I tell you, like, okay, an observer is standing some distance from a light pole, and I tell you how tall the light pole is. Let's go right here. So I could say an observer stands, I don't know, 10 feet from a light pole that is 30 feet tall. Find the angle of elevation, So find the angle of elevation between the observer, or I guess the feet of the observer, and the top of the pole. Now there's probably an angle of elevation question. Let me check in the review, but we'll do that one for now. Okay. So there isn't one of these in the review, so you're going to have to make sure you go back to section 5.1 and maybe look for some elevation questions. Okay. Alright, so you can draw a picture. So here's your little stick figure person. And say here's your light pole. And I told you that the observer is 10 feet from the light pole itself, and the light pole is 30 feet tall. And the angle of elevation is the one made from the base of the observer's feet, to the top of the light pole, so we're talking about this angle theta right here. So where do I want to go from here?
Take the tangent of theta.
Okay, so everybody agree with that, right? If I want to find this angle, I need to apply a trig function relating these two sides, so I like Reed's suggestion. If you apply tangent to that angle, now you need to be thinking SOHCAHTOA. This is a right triangle. Tangent is always the opposite side over the adjacent side, so that's the TOA, the TOA. So it'll be the 30 feet divided by the 10 feet, which would be positive 3. And then what do I apply to both sides to get the angle itself? Just apply your inverse tan or your arctan. And you'll get 71.57 degrees. Mostly everything I give you on this test, the angles are all going to be in degrees. Okay? And when you solve your triangles or you're finding angles in the triangles, you can just give everything in terms of degrees. Of course, you might need to think, if you memorized everything in terms of radians, it might be helpful, right? To know 30 degrees is the pi over 6, 45 is pi over 4, 60 is pi over 3. Okay, so that'd be an angle of elevation question. Yeah, Ocean.
Can we do number 50 on the review point?
Number 50? Okay, now I specifically didn't do any of these problems. I don't think I put any of these, for the most part, on the homework. So I'm not going to be doing the area of the property questions. There's a formula in 5.5 that I didn't talk about called Heron's formula for finding the area of parallelograms. So I skipped over that.
It's on the homework.
Was there one of these on the homework?
Yeah.
Okay, well then I'll have to go back and give everybody a point for extra credit. Okay, because I did not mean for that to be something I wanted to cover.
Yeah, because I was.
Figure out. You just went to view an example.
Okay. Yeah.
That's
okay though, I'll still give everybody extra credit for that one.
So we also don't need to know the 3/600 seconds in 1 degree?
No, I'm not going to give you anything in terms of minutes or seconds.
Okay.
Okay.
Good.
I know there was a question on the homework where they had you do it, and I don't think it was that hard to just go to the view example and see what you do. Because you just take the degrees and then you add the number of minutes over 60, and then you add the number of seconds over 3600. But no, I'm not going to put anything on the test with where you have to convert degrees, minutes, seconds to a degree metric.
Are we gonna have anything like 49?
Like what more?
Like 49, where it's like speed
There could be a 40 question like 49 if you want to go through one of those.
Yeah, I just have a hard time like visualizing it.
Okay.
Could we do it on our own a little bit?
On our what?
On our own kind of thing, like, and then we check, like, do like checks so that we can make sure that we understand it by ourselves.
What do you mean? Like, try it right now on your own?
Yeah, like for 2 minutes and then if you
Yeah, sure.
And then
Yeah, if you want to try, see if you can set up 49 on your own. It's really similar to that boat problem we did in class, where, like, if you have a force, like a wind acting on an object, and then the object has got its own speed and direction, then its ultimate speed and direction is going to be the sum of the forces or the sum of the vectors. Okay, so think about it for a couple minutes, and then we'll try 49. I'm just going to write down the information. I'm not going to solve the problem. So 49 on the review. So the airplane, does anyone need a copy of this? There are some people that came in towards the end. So an airplane flies 310 mph in the direction north 45 degrees west. One thing I want to tell you is you're going to do this from a top view, right? Like if my pen is the plane flying, everything we're doing is looking downward. Okay, so the plane's flying at a constant altitude. So again, just you're doing a top view. So if you're looking at north, south, east, west, the ground is going to be through the board, right? So the board is, you're thinking of the planes flying like on the board, right? And the ground level would be directly through the board. So like we're thinking of the board as being what we're viewing from the top. Just another minute, okay, Kirsten?
Yeah.
Okay. Just to keep things moving, I don't want to take too much time. Okay, so this is a vectors question. Okay. Now, what you're going to do is we're looking from above the plane, okay, right? So again, like imagine the floor is the ground, the plane's up here. We're actually looking from the top. Okay? And let's just assume that at some point, right? Let's just let this point represent where the plane is.
Well, shouldn't it be northwest?
Okay. Isn't that what it should be?
Yeah.
North. Okay. So first of all, what I'm going to do is I'm going to draw a vector representing the blowing wind. Okay, and that says that's 25 miles per hour straight to the north. So that's a vector going straight upward of length 25. So that's where the wind is blowing. And then north 45 degrees west. Hold on, I should have left myself some room because this vector, since the plane's flying 310 miles per hour, the vector representing the plane's direction is going to be 310 units long. So, okay, so here's the wind blowing 25 miles per hour, and then the plane's actually going in this direction, where this is a 45-degree angle, and that vector is length 310. Okay. Now, this is the direction and the speed the plane is trying to go, but the wind, since it's pushing upward, it's kind of going to change the direction of the plane. Now, the actual direction and speed are going to be given by the sum of these two vectors. Okay. I'm going to call this VP for the velocity of the plane. I'm going to call this just W for the wind. So I've got a wind vector and the vector representing the velocity and direction of the plane. And then if two vectors are joined at their tails, what geometric rule can I use to add those vectors? There's either the triangle rule or parallelogram rule.
The triangle.
So triangle rule is when you join the tail of one vector to the head of the other. If both vectors are joined at the tail, you're going to draw a copy of W over here, and you're going to draw a copy of the other vector right there. And the resulting vector that's going to give you the speed and the direction is going to be from the tails to the joining of the heads. Let's call this, I'm going to call this VG because they wanted the speed and direction relative to the ground. So that's the direction the plane's actually going to be heading because the wind is acting on it. Now you're going to need components of these vectors. I think the wind vector is easy. What's going to be true though is the actual velocity and direction of the plane is going to be given by the sum of the other two vectors. Okay. Again, some of you, you're going to learn this in physics. Some of you will, some of you won't. But the total force is always equal to the sum of the forces. Okay. So this is the force for the speed and direction of the plane. That's the force of the wind. And then the actual speed and direction is the sum of those two vectors. Now W, I think, is pretty easy to find its components because it's going straight upward. Okay, so what's the x direction of the wind vector? 0. The y direction is 25. So the wind vector just has components 0 and 25. And then we need to find the components of the vector VP. I'm going to have to go onto the side to do that. So I'm going to draw my little picture. I'm going to do it in the XY plane to help us see it. So there's my VP. Now if this is a 45-degree angle, right, I just need to find the x and y direction. How many units are we going to the left and how many units are we going up? And what we can do, we can use the angle inside this right triangle. I've now created a right triangle. If this angle is 45, well, what does the angle inside also have to be?
45, yeah,
That would also have to
too.
be, huh?
They're all 45 except for the angle.
Yep. So, right, this first quadrant, that's the x-axis and y-axis meet at a 90-degree angle. So this angle is also 45 degrees. Okay. And then you're going to have to use triangle trigonometry. If I call this, I don't know, you can call this, I don't know, I can even call it just x and y. It doesn't really matter. A, B, X, Y, Z, W. Okay, the letters aren't really important. You're going to solve for x. I also know that vector is 310 units long. The length of a vector is what's giving you the speed of the object. Okay, they told us the plane was flying 310 miles per hour. So what's a trig function that's going to relate this side to the 310? If I apply it to 45. So sine is actually opposite over hypotenuse.
Cosine.
Yeah, so we can do cosine 45 degrees equals x over 310. So x, you're going to the left 310 times 1 over root 2 units. Cosine 45 is 1 over root 2. And then you can do the same thing. Sine of 45 degrees is going to be y over 310. So y is 310 sine 45, which is also 1 over root 2. And that's going to give me the components of the vector VP. Okay, so the distance of this triangle, or the base, is really 310 times 1 over root 2, but really we're going in the negative direction. So the x component is minus 310 over root 2. The y component is positive 310 over root 2. Okay. So the speed of the plane gives you a vector, you can find its components. The wind gives you a vector, you can find its components. And then the actual speed and direction of the plane is the sum of those two vectors. Okay, so VG is going to equal, okay, well, we're going to add these two vectors together, so it's 0 plus negative 310 over root 2. And the y component is just going to be 25 plus 310 over root 2.
So that's the final answer.
Close, because we got to find the speed.
Oh.
The speed would be the magnitude of this vector. And I guess this vector is giving you the direction. Maybe technically you should probably say the angle that this vector forms. Like give some headings, like some bearing directions. Okay, so first of all, let's take care of the speed. The speed is the magnitude of Vg, which would be the square root of the sum of the squares of the components. Now I'm not going to do this one by hand. I'm going to plug this into the calculator because I don't think the arithmetic is very nice. Oops. Anybody do this yet?
I got 5. I don't know. How'd you get 5? I put it in parentheses. It just goes to...
I did too. I plugged it in how you did.
Oh, I forgot to put the squares. I'm so
I
tired.
got 292.8.
I'm getting 328.
I plugged it in how you put it in.
That was
Let me
7.
try one more time. So 310 over square root of 2 squared plus parentheses 25 plus
Oh,
fraction.
328.2.
You got 328?
Yeah.
328.
Yeah, that's what I got. So
Using y cosine, and that's what I got.
yeah, so 328 what?
328.2.
Okay, so initially, you know, the plane's got some thrust and it's heading in this direction at 310 miles per hour. Now, since it already has some north direction to it, the wind being 25 miles per hour to the north is probably going to increase your speed a little bit. The wind is helping you. Okay, so that's a sensible answer. Okay, and then the direction part, I basically am just going to come into my picture again. Or I'm going to draw a picture. So I now know how, so this is the actual, this is Vg, this is the vector that's giving me the speed and the direction of the plane after the wind has acted on it. And we know this vector is how long? It's now 328.2. And I don't know, I also know the components. I know this is, the x direction was 310 over root 2. The y direction was 25 plus 310 over root 2. If I find this angle right here, that'll give me the direction. Okay, I can say the direction is, and you can do your bearings, because this is going to be, I don't know, I can say it's north 90 degrees minus theta west. So starting from the north, we're rotating some amount of degrees to the west. So this little angle right here, alpha, is really giving me the direction. So it's going to be north 90 degrees minus theta to the west. And what can I do now? I can do tangent of theta is opposite over adjacent, do tangent inverse. Does anybody actually want to see me do that? Because this is now reduced to a triangle trigonometry problem. So you can do it together, but like I said, All I'm really doing is I'm using the components of VG. We went this many units to the left, this many units up. I guess we don't really need the speed or the length of the vector. We'll just use the exact values. But like I said, if you do tangent theta equals, if I call this y and I call this x, if you do tangent theta equals y over x, that theta will be tan inverse. And then you just, to get this angle alpha, you just subtract theta from 90 and that'll give you your directions. I would expect either a problem like this or a bearings problem. I can't ask you everything, okay, but do make sure you take a look at a bearings question. Make sure you take a look at one of these again. But all these problems are generally going to be the same. It's going to either be an airplane question or a boat question. You'll be given the speed and direction of the airplane. You'll be given a wind vector. Usually I'm pretty nice. I make it either go straight north, straight south, straight east, or straight west. That vector is pretty easy to find the components of. To find the components of the other one, though, you have to work a little harder. I'd come over to the side and draw a picture of that vector, and then use the bearings to find the angle inside the triangle. That'll give you the other two sides, which give you the components. All right. Any other type of thing? So that's good that we did one of those. I didn't fully finish it, but hopefully I gave everybody the recipe or formula for how to finish.
Can we go over triangles that might have more than one solution?
Yeah, like a side-side angle.
Yeah.
Okay.
What does that mean?
So yeah, make sure, and I put it on here, so if you look at the 5.3 section, there's 3 triangles you can solve using law of sines. Angle, side angle, angle, and then the one that has the ambiguous case, we call it the side angle.
Can I
Yeah.
just ask one quick question on the last
Yeah.
one? Is that supposed to be a negative 310 or a positive?
Well, if I'm just thinking of this as the side of a triangle,
Just the length.
we're just thinking of it as the
Okay.
positive distance.
So it should
to
be
the left.
positive. Okay.
Yeah.
Just making sure.
But when we write the components of the vector, since we're going in the negative x direction, we need a minus 310 over root 2.
Just making sure.
Okay, yeah, that's a good question.
The thing is the direction. Or is opposite.
Well, I'm going to use, I guess I could use theta because I could say west, theta degrees north. But typically, bearings are either given from the starting point being north or south. So if I really want to give the bearings, I need an angle starting from the north rotating to the west. So once I know theta, the bearings were actually given by alpha.
Okay.
And to find alpha, once you have theta, you just do 90 minus theta. I'm just following the conventions in the book. I wouldn't be that upset with you. I'd probably give you full credit if you just said west, theta degrees north. That'd also be okay. Remember, the first letter is just your starting direction, and then how many degrees are you rotating in this direction. But I'm just trying to follow the convention in the book, either starting with a north or south reference. Okay, so side angle. Oh, well, it's on the video. I'll get that posted today too. I forgot to push record at the beginning of class yesterday. I did make a Desmos video this morning. I'm uploading it right now to YouTube, so that'll be available this afternoon. Okay, so side angle. Let me make something up here. So let's say we know alpha is 40 degrees, and I give you that this is 6 and this is, I don't know, 7. Well, let's do 8. So that's a side angle triangle. And then I'll just label these gamma, beta, and C. So let's solve the side angle triangle. Now ultimately, what's the big mistake you want to avoid on these triangles is SOHCAHTOA will not work unless the triangle is a right triangle. So like trying to say sine is opposite over hypotenuse or so on, that doesn't make sense in oblique triangles. Okay. So in that case, that means you have to use law of sines or law of cosines. Okay. So let me see what we are time-wise. Okay. So what can I do first here? I'm going to try and find a first angle, see if a triangle even exists at all. Okay, so I don't think I can find this angle because I don't know the opposite side. So I think the first angle we have to find is beta. So we can do sine beta over 8. So remember, sine of an angle over its opposite side equals sine of any other angle over its opposite side. The only pair of opposite angle and opposite side we know is the 40 degrees and the 6. So this would be sine 40 degrees over 6. And when you solve for beta, it's going to be sine inverse of 8 sine 40 over 6.
There won't be an issue that that's...
Yeah, Ocean?
For angles in this case, do you want us to just round to the nearest degree?
I'll tell. This time I'll actually tell you on the test. But yeah, I'll probably do something like nearest degree or nearest tenth. Yeah.
So not an issue because beta is the largest angle.
So.
Using sine. 'Cause yeah. I don't know how.
Yeah, there might be an issue here with trying to use beta. I guess I set it up in such a way that I made that the largest angle, unless C actually ends up being the longest side.
But we can't use law of
We can't use law of cosines because we don't have enough information. You know what I can do to fix this though?
Switch A's.
There we go. Now I don't have to worry. And generally, I don't like doing that to you. I probably am not going to give you a triangle where the first angle you have to find is the largest angle. Okay, so just switch the 6 and the 8. That way I think this will actually work and give you at least one possible triangle. Make sure your calculator's in degree mode. So I get, see if I get the same thing as everybody. Here, I'll just do 1 decimal place. I get 28.8 degrees. So that means there does exist at least one triangle. Okay. So before we see if there's a second one, let's just find the rest of the sides and angles in this triangle. Okay, well I think now that we know beta is 28.8 degrees, I think we can find gamma pretty easily, right? Gamma is going to equal 180 degrees minus those two other angles. And anybody get this one yet?
111.2.
What is it?
111.2.
So that's 111.2. Now, is my picture really accurate?
No.
No, but that's okay. Right? We're just drawing the picture to help us relate which sides are related to other angles and sides. So it's just to help us set up the equations. And then, now I know this is 111.2 degrees. I can find the length of C. Now, could I technically use law of cosines here if I wanted to?
Yeah.
I could, but really there's no need to if I already have law of sines. Okay, but here you have a choice. I could use law of sines or law of cosines. So I think if I use law of sines, I'll do it this way. C over sine 111.2 degrees. And I'm actually just going to use the original angle inside we already had. So I'll do 8 over sine 40. So C equals 8 sine 111.2 over sine 40. And anybody spit that out yet?
11.6.
You get 11.6. So that would give me one of the triangles, if there is more than one. Okay. Now, if you're going to find a second triangle, okay, it's going to have the same alpha, A, and B. So those are going to stay the same. The only thing that might change is you might get a different alpha, beta, and C. Okay. So what do I find first? You'd have to get out your little guidelines for what to do to possibly find a second triangle. Now, which angle did we find first? We found beta first. Whichever angle you find first, you find that corresponding angle in the second triangle. So what I'm going to try and do now is find beta 2 in a second triangle, and what would that one be? Yeah, if there's a second triangle with the second beta, it's going to be 180 minus the first. That's 180 degrees minus the 28.8. And what do you end up getting? What is it? Okay. And then, remember, the given angle has to be in the second triangle as well. But what's the problem this time? Yeah, right? If I take this angle plus the angle that's supposed to be in a second solution, so notice alpha plus beta 2 is 40 degrees plus 151.2 degrees, which is 191.2. That's greater than 180. So no second triangle exists. Right? Basically, the idea is if that's going to be in the second triangle and that's supposed to be another angle in that triangle, there's no room for a third angle because those angles add up to more than 180. Okay. If that was less than 180, you would be able to find your gamma 2, and you'd be able to find your other two sides. Actually, sorry, your other side, because you already knew two of the sides to begin with. Okay, does that kind of help the process? Okay. Any questions? Other questions? Okay, we still have about 8 minutes, 10 minutes if people don't mind giving up 2 minutes. If your next class is in this building, I find it hard to believe that 8 minutes isn't enough time to get there, unless you have to go to the mechanical building or something. Anybody ever have classes in the water center or anything?
I go there to work.
It's a good place to study. It's nice and quiet over there. You work over there?
I work everywhere. Computers. So.
Oh yeah, you gotta work on computers.
Wherever there's a computer, I work.
Okay, so we did a law of sines. Law of cosines, remember there's only two types of triangles, side, angle, side. And then there's side, side, side. Yeah?
Can we do another dot product?
Yeah, we should probably do dot products. What specifically? I mean, we did the application one. Now, do you want to do I can give you 2 points in the plane and you can find the vector between the points?
Yeah.
Okay. And then if we have time, we can also do a find the angle between two vectors question.
Find the angle one first.
Okay. So let's find an angle between two vectors. So find the angle between the vectors u equals, I'll just make something up, 2, 3, and v equals, now I gotta think so it's not stupid. Okay. And let's do v equals negative 4, 6. Okay. So let me remind everybody, there's 2 dot product formulas. So one is the dot product would be u sub 1 v sub 1 plus u sub 2 v sub 2. That's where u is u1, u2, and v is v1, v2. Okay. So one is just multiply component-wise and take the sum. So it'd be the product of the first components plus product of the second components. And then remember, the other formula for the dot product is the product of the magnitudes of the vectors times cosine of the angle between them. Now, which formula is actually more practical to use to calculate a dot product? Like if I actually just want to know what the dot product is, the first one is more useful. The second formula is really only useful to help you find the angle theta between the vectors. In that case, you'd have to divide both sides by the magnitudes and take cosine inverse. So you'd get u dot v over magnitude u, magnitude v. So you have to calculate three things. We need the dot product, and then we need the lengths of each of those vectors. So we'll do the dot product first. And what do you do again? You multiply the x components. So 2 times negative 4 plus 3 times 6. That's negative 8 plus 18. I think we get positive 10. Also, just to give everyone an idea, 2 units right, 3 units up, maybe this is u. And then 4 units left and 6 units up. Here's v right here. We're trying to find this angle theta between those two vectors. That's just a rough sketch of what it looks like. Right, u's in the first quadrant, v's in the second quadrant. Okay, so the dot product is 10. And then what's the formula for the length of a vector? Remember, it comes from Pythagorean theorem.
It'll be 2 squared plus 3 squared.
But what's the formula though? So it's always the square root,
u1
and then you take the components and
square them
and add, right? So you do 2 squared plus 3 squared. The idea is that, right, the length of the vector is just the hypotenuse in a right triangle. So you just remember the hypotenuse squared is the sum of the other two sides squared. And when you solve for the hypotenuse, that's where you get that square root. And then 4 plus 9, you're going to get square root 13. So the length of a vector is just the square root of the sum of the squares of the components. Magnitude v is the square root of minus 4 squared plus 6 squared. Remember, you're squaring a negative. Make sure your negative number's in parentheses because it will become positive once you square. And I think that's what, 16 plus 36? So you get the square root of 52. I think that's 4 times 13.
Yeah.
So this should be 2 root 13. We okay there? So if you want the angle between the vectors, you need the dot product. Use the formula from the theorem where you multiply components and add. And then you also need the length or magnitude of each vector. And then when you're done, you just plug it into this formula, cosine inverse. The dot product was 10. And then you have root 13 times 2 root 13. Which I think root 13 times root 13 is 13 times 2 is 26. And I get, well, what did other people
I
get?
got 67.38.
67.38, you said?
Yeah.
Okay. I think that's correct.
Cool.
That would be the angle between the two vectors. Yeah?
Would you mark that on the dot side for 52?
No, but you're certainly going to see me write this on your paper, but I'm not really that picky. There's 2 minutes left. I want to do one thing. Because this was your second question, or maybe another question with vectors you might get.